Good morning. My name is Steve Yokum. I'm with NASA, IV&V facility. Today I'm going to do and talk about Aristotle. Aristotle is Artemis all software. Some of you probably don't know what Artemis is, so Artemis is NASA's Return to the Moon initiative. That's the space vehicle, the ground system. Eventually it'll involve gateways orbiting the moon and other things, but those are to come in the future. Aristotle is the all software emulation of Artemis. Additionally, we have it compressed so it runs on a single laptop environment. So a little background on where we're from, Aristotle, the overview, the architecture, some things in the future, and then I'm going to do a fly-out demo of the Artemis mission and show an abort happening mid-flight. Again, some of you may not know what the IV&V facility is about of NASA. Any of the large NASA software missions come through us. Certainly anything that's manned, we do verification on the flight software. My colleague John's presenting this afternoon. He'll give you more details. So I actually work for a support team called JSTAR, and what our bread and butter kind of is taking these large missions, James Webb, as you see here, and emulating the flight software, simulating the sensors, the actuators, the dynamics, and compressing this all down onto a single laptop environment. We call this the digital twin. We also generally support the ground system as well. So we can command the vehicle, we can get telemetry, we can essentially run the whole mission in pretty good fidelity generally because we typically are running the true flight binary. Not a recompile. If it's a PowerPC, we run the true PowerPC binaries. So Aristotle, what is it? Obviously, it's a real fancy backronym. I couldn't tell you what this stood for unless I was looking at it right here. This seems to be a Greek theme with all the components, so we just stuck with that and went with Aristotle. So it is that vehicle you see here that is what's going to take us back to the moon. It also encompasses the ground systems. Right here we see the firing room down at Kennedy Space Center. So a little review of what all is in this vehicle and where is the flight software. So get the mouse working here. So up top we have the crew vehicle. That is where the 4 astronauts will be. There's flight software there that is provided by Lockheed Martin and their simulation called Socrates. ICPS is the second stage right here. That is a ULA product. That's their flight software. SLS is the core stage. That's the main engine here and the 2 solid rocket boosters. There's flight software there. So there's 3 pieces of flight software that compose this vehicle. There's also the launch abort system that shrouds Orion that is attached before Orion gets to orbit, so it can pull that vehicle off safely if there's an anomaly in flight. It only has an FPGA, no flight software. Additionally, you have your traditional systems we've had for 50 plus years. You have Kennedy, which tanks the vehicles, does all the setup, all the prep, all the pre-launch checkouts, ultimately launches the vehicle. Once it clears the tower, Houston takes over. Artemis is a phased approach. We did Artemis 1 last year. That was very successful. We orbited the moon with the Orion vehicle. Artemis 2 is coming up next year. This will be the first time we actually have astronauts on the vehicle. That is also going to orbit the moon and come back. Artemis 3 is when things get really exciting. This is where it's quite a bit different from how things were done in Apollo. NASA's vehicle takes us out to the moon, but then SpaceX is also joining up with us there. We dock with SpaceX. SpaceX actually takes the astronauts to the lunar surface. We'll relaunch from the lunar surface and come back to the Orion capsule dock, and then Orion brings the astronauts back to Earth. Artemis 4, there's a new second stage that's going to be going here. This will be a NASA second stage. A lot more powerful. The flight software is actually going to move up to this second stage, so the whole vehicle will be controlled by the second stage at that point. And one of the goals of Artemis is to dock with this new gateway that's going to be orbiting the moon. So where are the simulators here? So we have virtual machines that emulate all those components I just talked about. So the SLS core stage, this is an emulation. The Orion capsule is an emulation, and then the Kennedy ground system is another emulation. We have that in 3 virtual machines. Those virtual machines are then integrated together and communicate on a single platform. The ICPS, unfortunately, NASA does not get the flight software, so we are limited there. So we're just pushing a flat file trajectory file through that to do our full flyout. When that gets replaced, that'll simplify things a lot for this simulation. So some of the unique features that we have, and I'm going to skip forward one slide here. So what you typically see at NASA, and this is the 4 systems being tested together. You have SLS, the first stage, that's called a shade. ICPS, the second stage. Orion, the crew stage, and EGS is the ground. These are all in your, typical $1 million racks. Those are all tied together with hardware ScramNet. ScramNet does the simulated data and the timing to keep everybody in sync. The flight buses are typically done with Ethernet to do telemetry and commanding. And so this is, your expensive lab that you have scheduling constraints and whatnot. If you want one of those cool NASA racks, you can find one of those on OpenAI. It drew some real cool racks there. So how are we unique? So we can run what we just saw on that slide on a single laptop. Now there's one big constraint here, obviously, and that is we can't run real time. We only run about a quarter real time, but so do the sensors, so do the actuators, so do the back-end dynamics. So the flight software really doesn't know that it's not running in real time. Takes a pretty beefy laptop, 128 gigs of RAM. These virtual machines really eat up a lot of memory. We unlike the project, can run the true SLS binary in full triplex. So it's there's 3 flight computers. We run them all in sync. We virtualize the ScramNet. We provide a flyout. I'm going to show here is my demo that you can visualize the flyout. And then EGS, we had to do a lot of things I'm going to talk about later to make that work in a simulated environment. Here you see what's in orange represents virtual machines. We use VirtualBox to virtualize our machines. The ScramNet synchronizes those machines. I'll talk a little bit how the ScramNet was done. The typical flight buses between components of Artemis was 422. So we use UDP to do that. The flight buses were already Ethernet, so that was easy to emulate. And then we feed this data over to a visualization so we can see it as it flies out. So ScramNet, like I mentioned, obviously in an all software, you can't use ScramNet because that's a hardware protocol. So we've made mods to the Linux kernel in each of those virtual machines, and we do that as a UDP broadcast. Any of the 422 data, that's just UDP point to point, and as I mentioned, command and telemetry is Ethernet, so that was pretty easy to get working. So what can we do special being in this all software environment and on a single laptop? So in IVNV, we don't look so much at the happy path of the flight software because we know everybody's testing the happy path. So what we really focus on is the faults. You know, if something goes wrong at T+2 and we're just clearing the pad, can we abort the astronaut safely at that point? We're going to test those scenarios heavily. And being all software, you know, we can change what's going into an interrupt handler if we want. We can hook up a GDB and step through the software. So we have unique capabilities that the projects at the whole don't typically have. Just as an example too, we can do code coverage, so we can run a mission through, and then we can collect the data and run that through tools that highlight all the code that was run in green. So if I want to run an abort scenario, okay, what code was actually running for this abort scenario? I can look at that software and go through it and see what of the C++ was actually executed. But the truly big thing about this laptop thing is it virtually costs nothing. I mean, you can get a lot of flight software into a lot of people's hands, and that's really the big bang here. Is we can share this with, you know, pretty much anybody that can have a laptop, so we can have a lot of instances of flight software running cheaply and without any schedule constraints. So, like I said, there's 3 virtual machines that make this up. Talk a little bit about SOS. There's NASA Marshall develops a sim called Artemis. That's all caps Artemis. That's an acronym. That's not the whole program. So we take that. We've replaced their Linux recompiled flight computer, put in a SIMX model that's full triplex. There's a lot of data that comes out of these systems off the 422 and 15.3 buses, all the telemetry. That creates gigs of data for a single 10-minute flyout. We have this neat tool called Mesa that helps us visualize that data. And lastly, this just came about recently. Typically, you always strap an explosive to these rockets, and you have a range officer that can hit a button and blow them up if something goes wrong. Lately, the Space Force has been moving away from that, and they're going to an automated flight termination unit. Artemis and NASA want to do the same, so Artemis 4 is going to fly an AFTU. We recently got that software, and it worked out well. It's a Geisler board. We're doing a QEMU solution for that, and that'll be integrated into Aristotle here shortly. Socrates, this is the product from Lockheed Martin. We don't do a ton of this. We do a lot of configuration. We run the second stage actually within this VM. That's where we do our flat file trajectory as part of the flyout. Socrates has, but it also has the really cool astronaut displays, the displays the crew use to interface with the vehicle. They have some control capabilities they can abort. I wanted to show those today as part of my demo, but unfortunately I realized they were ITAR, so I cannot show those. And then the ground system, those bullets in brown there, I've actually done a presentation on each of those. Those get pretty involved, but that was an AIX. We had to get it to Linux. We had all kinds of big Indian problems to deal with there. We run the PLCs. That was really complicated because you cannot run PLC software on anything other than a PLC. Ladder logic does not port to anything, so we translated with Python all that ladder logic into C code so we could run it on Linux. And then ground systems don't typically run in sim time. So when I said we run in a quarter real time, ground systems don't want to play nice to that. Ground systems only want to run in real time. So we tricked out the Linux OS through some LD preload tricks and changed the timers and the sleep so it runs in sim time instead of the Linux real time. Again, same problem before. We can show all the displays that the crew down at the firing room see. We can run all those telemetry displays, the commanding displays. I was going to show those today too, but they're all ITAR, so I can't show those either, unfortunately. So dealing with all these virtual machines can get a little laborious. There's a lot of clicking and setting things up and collecting telemetry from different sources because there's separate virtual machines. So we developed this Windows GUI that runs on the host OS called AStart. It allows you to initialize the virtual machine, so it'll bring up all the VirtualBox instances. It will start them. It's basically your test conductor. And from this single GUI here, you can collect telemetry, you can do commanding. It also has a scripting tab, so you can control your scenarios when you want to send commands, what telemetry you want to collect specifically. I mentioned we have the ability to visualize the flyout. We use the Unity game engine to do that. That's what I'm going to demo here in a minute. So, you know, in a way, this is just the good eye candy, but this is a neat tool if you don't always want to dig through the telemetry, especially if you're doing aborts. You can see the thing fly off the nose, and so yeah, it beats digging through telemetry every day for the testers. So wrapping up here is where are we going in the future? You know, what I'm going to show today is the flight software for Artemis 2. That's the mission that's coming up next. We got to get to Artemis 3. We got to get to Artemis 4. So we've got to build docking into Aristotle. We got to work with the gateway. HLS is the SpaceX component. We got to deal with, you know, what happens on the lunar surfaces. So there's quite a bit coming here in the future and a whole lot of work to do. So, going to do a demo now. If you want that cool NASA clock, you can also make that on OpenAI. So let's see how I do this. I need to share. Okay, I'm sharing. Oh, no.
I did that.
Okay. Okay, I think it's up there.
Okay. Let me go to full screen.
Okay. So what I'm going to demonstrate today, and let me superemphasize here. I'm not showing a movie of the Artemis flyout. So if you want to see a really nice graphical movie, you know, go on YouTube and you can find that here. This hooks up to the simulation. So it is the, you know, honest to God 1523 flight software that SLS is flying. Same thing's running here. So that's what's being displayed here. I'm not running that today. I'm picking that from a telemetry file because, like I said, it runs in a quarter real time, and no one wants to watch a demo in quarter real time. That would get boring. So what I did here is pulling from the telemetry file. After the SRBs, the solid rocket boosters separate, Houston is going to command an abort. So something went catastrophically wrong. The launch abort system is going to pull the Orion capsule off, and that's what we're going to watch here. You can see the MET, the mission elapsed time, so, you know, that's your negative number. That'll hit 0 at launch and progress. The segment, that is something that Orion flight software produces, so it moves incrementally through segments. It'll be as events happen. So those segments are our trigger to do things, separate things with the vehicle. So we get in the 200s, that's SLS flight. We get in 300s, that's second stage flight, and so on. Aborts have their own special set of numbers. So you'll see the names change down there as we progress. And of course, altitude is just kind of interesting about where we are at the moment. So going to play this, and because I'm recorded, I can do faster. I can step that up to 2x and 4x real time, so I'll make this run a little faster. So bump this up to 4x for right now. So what that vehicle, so we're collecting the position and attitude. So it's pretty much just X, Y, Z and the quaternions, and that's what we're using to visualize what you see here right now. And this is the true, you know, SLS trajectory it's producing from the Aristotle simulation. Now it's, so about 1:30, I'll slow this down a little bit, we're going to see the SRBs shut down and come off. So now you just have the RS-425s running here at 1:48. There's going to be this catastrophic abort. There it was. So now you have the launch abort system pulling, it's shrouding the Orion crew capsule. You can see we're now in a segment that signifies abort. The altitude is still increasing. So now the launch abort system came out, so now the Orion capsule is in free fall. Altitude's still going up, so there's some inertia there. but I think it'll start falling soon. You see the Florida coast coming into view there, so we're safely over the Atlantic Ocean at this point. The next thing that's going to happen is the chute's going to come out around 4:50. Let me advance time a little bit more there, a little quicker. So yeah, you can see altitude is now falling. So this we never had to do an abort any time in Apollo. They had a very similar launch abort system. We hope we don't ever have to do a launch abort any time in Artemis as well, but of course this is a very important feature of the flight software that we do extensive testing on, especially at IV and NASA IV&V, since we look at the fault cases, so we do a lot of testing on this particular scenario. Where you abort from, be it the pad, be it at T+10 or, very close to orbit, very different things happen in the abort. There's cases where it has to take it all the way around to San Diego. So we didn't have a parachute model, so this is pretty cheesy, I'll have to admit. So, but, we're just testing here. We're not trying to, like I said, this isn't a movie. So now we're in drogue descent. I will speed this up because this isn't very interesting. But you can see the dynamics acting on the vehicle. Eventually we'll get to negative. I think 2 or 3 will hit the water. I don't have a simulation of the water, so you're not going to see a nice splashdown or anything here. It just hits the water, and so we've hit the water. We're sitting in the water waiting for the Navy to come and get us at this point. But everyone's alive. We got off the vehicle, so everything's good. Okay, so that wraps up my presentation and demonstration. Do I take questions?
Yeah.
Okay.
There's some questions. Okay. I'm going to start because I know that there's some online questions. Apologize if these have already been answered. So from Matthew Benson, where is time condition to maintain synchronization of all the various components? Is it at the flight software level or virtual machine level or emulated hardware or something in between?
Yeah, so that's a good question. The ScramNet, the way this is architected, and this is the way we do it, and this is the way, also the program does it, is the ScramNet does the timing. So, and it's a ping pong effect. So I'll run my, SLS will run his frame, and he'll tell Orion, I'm done, and pass him his sim data. Then Orion runs his frame, ping pongs back to SLS. So it just ping pongs back and forth, and whoever's running the slowest, that kind of ends up being the sim time. So in our case, SLS is the slow piece, so that's why we're a quarter real time. Actually, when SLS separates, we can run it out double real time at that point. But it's a ScramNet ping pong that sets the sim time.
Great. Question?
Hi, I may have missed it earlier in your presentation when you mentioned it, but is Unity being used for mostly visualization of the telemetry file, but not necessarily simulation of actual physical simulation?
UDP is used for the...
the Unity game engine.
Oh, I'm sorry, what's the question?
Is Unity being used mostly for visualization of the telemetry data?
Yes.
Not actual physical simulation?
No,
Okay.
It's strictly a visualization of the telemetry.
Okay,
There's no dynamics, there's no math being run here whatsoever. It's just collecting position and quaternions and visualizing that from the telemetry.
Thank you.
All right. We've got a ton of questions online. Any? Okay. Let me do one online and then I'll go back there. I don't know if this got answered. Do you use hardware acceleration for the flight displays? If yes, how do you simulate its software stack?
We do not use hardware simulation for the flight displays.
Yeah, this is Josh from Stoke Space. Can you speak to what level you're simulating the world? Is that on you guys? Are you on the hook? Like, where does your sensor spoofing come from, et cetera?
Simulating the world. I'm not sure what you mean by that.
Like, it sounds like you have bunch of flight software that's running on your computer, and then you end up with a telemetry file of the result of the flight. Like, where's the other side of the sim coming from?
So in the virtual machines, take SLS for example, they have, you know, all the back-end dynamics that are running, the equations of motion, the world, whatnot, and doing the fly out, and, you know, they have a point in space that their trajectory needs to hit. So that's where all those dynamics are being generated in one of those virtual machines. Now, as far as the Unity visualization goes, this isn't really my piece so much, but, you know, I just know we've had to do translations from their ECEF coordinate system to whatever coordinate system Unity uses, and, you know, map that XYZ so it shows up correctly and the world shows up correctly to visualize the flyout. I don't know if I answered your question very well, but hopefully we can talk later if not.
Another question in the back.
What is your turnaround time for if there's like updates to flight software or different components? How quickly can you get that updated?
Yeah, that depends. So these sims, you know, the one from Lockheed Martin, the one from SLS, they're EGS, they're very different, and that time frame is very different in result. So for SLS, it's really quick because we run the true flight binary. We can just drop that in and we can push out a new SLS simulation in probably one day. Socrates is a complex beast, and that probably takes a week to get that integrated and push out a new flight software version. And then the Kennedy ground system is a very complex beast, and that can take up to a month to push out a new, what they call TCIDs. So if we want to push out a release that's just the vehicle, it's probably a couple weeks if we get new flight software.
All right. So I'm going to take another online. Can you give a sense of the effort involved in this digital twin work, ballpark size of team implementing, and how long it's expected to take?
Yeah, so we're a pretty small, lean team generally. We're looking at probably 5 to 6 people putting this together. But as you can imagine, these things are multi-year efforts. We originally started with just the CIMIX model of the SLS flight software. I don't know, Scott, was that 5 or 6 years ago, probably? And we've been iteratively building this up as we get more. You know, we depend a lot on the contractors. As Lockheed comes out with new products and enhances their sim, then we roll that in and make our simulation better. Same with Boeing and ULA and whatnot. So, you know, this has been developed over 5 to 6 years, but with a very lean team, as NASA IVNV just does not get the budget everybody else does.
Okay, so I think we have time for one more virtual, and if anybody has one, I'll come out to y'all. What is the biggest bottleneck in the full virtual stack that restricts it to quarter real time? If you were to re-architect from the ground up, what would you change and keep the same?
Fantastic question. So the bottleneck is the triplex SLS flight computer. We run the true flight binary, which is awesome, but we also run it fully triplex. So there's 3 of them and they run in lockstep. That's awesome, but there's also a big hit to that. So they have a cross-channel data link, and they have extremely tight timing across that data link. It's in the microseconds. So to make that work in CIMIX is a virtualization engine for hardware, for those of you that don't know. We have to context switch between those 3 flight computers at an extremely high rate. And that context switch is what slows the entire simulation down by doing that. So to get the fidelity, we take a huge hit on performance. And what would I do if I did that again? I would make the effort. So people tested the triplex at one point, but they don't do that anymore because it's well established. We'd make the effort to run simplex and get rid of that need for the triplex. I'd still like to go simplex and get more performance back, but the components within that vehicle talk to 1553 buses that connect to only certain flight computers. So getting rid of the full flight computer setup has some complications. So, but I would put more effort into that, getting to simplex in the back end.
All right, this is the last question.
Andre Choi with Aerospace. So within your IVNV platform, and you mentioned it's going to be like a binary executable code, you can drop it in, but how do you work out the interfaces? Because every vendor will have different interfaces, or?
What are the interfaces to flight software?
Right. I mean, if different vendors come up, they have different interfaces, right?
Well, the interfaces are fixed. You know, when we get the flight computer, it has, you know, speaking to SLS, the only interfaces it has is 1553 bus and 422. So whatever sits on the other side of that, well, I don't really care. I can talk 1553 and I can talk 422, so I can support those interfaces.
Got it.
So I'm only constrained about those buses that attach to flight software.
Gotcha. Thank you.
All right, thank you, Stephen.
Thank you.
It was a great demonstration. Appreciate it.